So, welcome back to the course on architectural design of ICs. So, in the last class we have seen the architecture about multiplier design. So, how efficiently we can design multiplier, so that we have seen. So, we have seen sign multiplication and then unsigned multiplication. What are the architectures? Some of the architectures are that means they have been used for area optimization, and some of the architecture has been used for speed optimization. So, that means in some of the, actually it depends upon the application, that means for which application I am designing or I am intending to design the circuit or that particular multiplier. So, depending on that we choose different kind of architecture. Okay. So, and then we have seen that array multiplier architecture too, where there is a regular structure, that means the data flow on that particular structure, it is very much regular. So, that type of architecture, different kind of multiplier architectures we have already seen. Okay. So, then another point is that suppose we need to do squaring. So, squaring is another, that means that is another form of multiplication where we multiply with the same numbers. So, we have seen till now whatever is the number we have seen, that means the multiplier and the multiplicand, they are two different numbers. Okay. So, considering that fact, then we have gone for the different architecture for that. Suppose the two that means multiplier and multiplicand both are same. So, at that time can I do more optimization on the circuit so that that it becomes hardware efficient in terms of, that means that area as well as the power as well as the speed, can I improve it if I am doing, that means if I am multiplying the same number with it. Okay. So, that squaring circuit now we will investigate on this today's lecture. Okay. So, this is the squaring. So, suppose I have to multiply x with x. Okay. So, now consider x are of 5 bits. Okay. So, x0 to x4, then the same number has been multiplied with is x0 to x4. So, the just like the same multiplication algorithm, whatever we have seen, it is just bitwise multiplication initially. So, bitwise multiplication means x0 will be multiplied with x0, then x0 into x1, x0 into x2, x0 into x3 and x0 into x4. Then again it will be, whenever I have to, that means I will go for this next bit, at that time it will be started from 1 bit left shift. Okay, as the position is 1 bit shifted. So, depending on the weight of this particular position, now I have to start from here. So, just like the same, I will get, or I will get, that means I will form the partial products. So, whenever we are now actually in multiplier, what we do, whenever we got this partial product, so after that what we do, that means this column wise we just add it. Okay. So, that different the addition method, how I will add, that is different depending on different architecture. But here, so before to that means do this addition of these partial products, what I can do, that means here if you just investigate or if you just closely look, that x0 into x0, if I multiply x0 with x0, that will be nothing but your x0. Why? Because if I multiply a with a according to the Boolean function logic, so that will be a. So, in the next column, if you see what I am doing here, x1 into x0, x0, x1. So, this is nothing but x1 x0, x1 x0. So, if I add x1 x0, x1 x0 twice, so at that time what it will be? It will be 2 of x1 and x0. So, 2 of x1 and x0 means this position, now this x1 and x0, this I can write at the next corresponding left hand side. Why? Because this is the position with weight of multiplied with 2. So, that means if this is the weight, binary weight for this particular position is 2. So, then this particular weight of this particular position, that is 4. So, that means this 2 is multiplied with another 2. So, 2 of x 1 and x 0 means this x 1 and x 0 can be written here instead of this particular position. Okay. So, that means I do not need to add this x 1 and x 0, that means I do not need any addition operation to, or this ORing operation to calculate this x 1 and x 0 plus x 1 and x 0. Just like the same, I can remove, or I do not require the AND gate, which is basically doing this x 0 multiplied with x 0. Why? Because x 0 into x 0, that is nothing but my x 0. So, the direct x 0 can be mentioned as P 0, or which is the, that means the product 0th product bit. Okay. So, in this way, if I investigate this whole term, whole partial products, I can get some of the optimization factors. Okay. So, what are that? Like if I have to add this xij with xji, so that will be, that means as this becomes xij plus xij, or xji or xij, both are same. So, that will be mentioned as 2 xi of xj, xi and xj. So, that can be written as the xi and xj, that can be written on the next MSB position, or that will be shifted to the next MSB position. Just like the same, what I said just now, that xi, if I want to multiply with xi, that will be nothing but my xi. Now, suppose I have to add these particular terms xi xj plus xi. So, can I reduce this term? Yes, I can reduce, or I can write these particular terms in a different way. How? If I write this xi xj plus 2 xi in this manner, that is 2 xi xj minus xi xj plus xi. That means 1 xi xj has been minus from this 2 xi xj. So, 2 xi xj plus xi is common over here. So, I take it common and it can be written as 1 minus xj. So, 1 minus xj is nothing but xj bar. So, that means now this xi xj plus xi, that can be written as xi xj bar at this particular position, and as this is 2 xi xj. So, that means this will be shifted to the next MSB position. So, that is why this xi xj has been moved to the next MSB position. Okay, got it? So, that means these particular terms xi xj plus xi, that can be written as now xi xj in the next MSB side, whereas this xi xj bar on the corresponding whatever, that means position we are trying to add this xi xj plus xi. So, on that particular position this can be written. So, that means this kind of optimization we can do whenever we are doing this squaring operation. Okay. So, that means now as I am removing some of the gates using this kind of this logical optimization. So, that means now I can save more number of gates. So, saving more number of gate means I can reduce the complexity, logical complexity, and reducing the logical complexity, which will give me in terms of savings in terms of power consumption, as well as sometimes the improvement in the speed too. Okay. So, this is not the fact that all the time I will get the benefit in terms of speed, I may not get, but here I can get in terms of improvement in terms of speed. Okay. So, then there is another method of doing this squaring. So, this is that means generic method for multiplication, which we have already followed for doing this squaring operation. So, another thing also we can do, that means that is as the number is basically fixed, means the number is same. So, that means a number is same means the number can be either 0, 1, 2, 3, 4, 5, 6, 7. So, that means any decimal number, and squaring means it will be just 4 will be multiplied with 4 only. Okay. So, what we can do? We can store this particular squared values in the ROM or in a memory, okay, where you can see that this 0th location contains the values of 0. This 1 location of the memory contains the values of 1. Then second location of the memory contains the values of 4. Then 9, then 16. That means here this is the address values. This is the address values means, so this is the 0th location, this is 1, this is 2, second location, this is third location, this is 4th location, something like this. If I want to choose, that means this is this for k bit, if I, that means if the ROM size is of that means k bit, okay. So that means now I can, sorry, this input is of k bit. So that means now I can form 2 to the power k minus 1 number I can get, okay. So and this corresponding, this ROM can store the values of 2 to the power k minus 1 square values. So that means if I chose this k bit for the input, so that means the length of the corresponding ROM size will be 2 to the power k minus 1. Not only 2 to the power k minus 1, I need, this will be basically 2 dimensional. This ROM will be 2 dimensional. How it will be 2 dimensional? Because to store this 1, 4, 9, 16, this value, I need the numbers will be represented or stored in the ROM in terms of binary. So that means for one of this location, this value contains, the location value contains, let us say 1, okay, and but this corresponds, this particular value that may be contains of 16 bit, okay. So that means if this is the, if this is the, that means 2 to the power k minus 1, so twice k bit I require, okay, to store this particular 2 to the power k minus 1 square values. Why? Because if you see that, just see, if for considering this 2, okay, so the consider, if you consider 2, so that means now I require the number is basically squared, that means that is 4, okay. So that means to if I consider k number of bit for this, I need 2 to the power k minus 1, sorry, 2 to the power k number of positions, or the length of this ROM will be 2 to the power k, along with that each of the length of this twice of k bit each. So that means now if my k is more, if I consider the k is of, that means in a wide range, so at that time the corresponding ROM size will be very much high. So very much high means it will consume more power, more area as well as more power, okay. So that is why this particular, this lookup table based, or this is ROM based, or I can say this is as lookup table based. Lookup table means where we store the values, okay. So this lookup table based this squaring circuit, it is useful whenever the values of k is relatively small. For higher values of k, we can, that means instead of getting the, that means here what is the advantage? That means we do not need any computation, extra that means the complexity of the circuit, that will be reduced, because it is just stored. So I will fetch the data from the memory only. So if the corresponding, suppose the input is, let us say, let us consider 3, so automatically the 9 will be retrieved from the memory. So the complexity wise it is very much simpler, okay, in compared to the previous circuit. But the thing is that as the k value will be more, so that means I require more area as well as more power. At that time the advantage, though the complexity will be lesser, but the consumption of area and power, that will be on the higher side. So, on that particular case it is not that means suggested to use this kind of architecture for squaring operation. Okay. So, then how we can do this multiplication using this squaring? So, how we can do this multiplication using squaring? Suppose I need to multiply a into x. How we can do? We know the fact that actually this is the basic arithmetic we have learned in our high school days. So, that is a plus xs whole square minus a minus xs whole square divided by 4. So, that I will get ax. Why? Because here what I will get a plus x of whole square means a square plus 2ax plus x square minus of a square plus minus 2ax plus x square. So, minus a square minus x square, that will be, that means nullify from the here. So, 2ax I will get here and 2ax I will get from this particular things. So, 2ax 4ax divided by 4 means that is nothing but ax. So, division of 4 means if I just discard the last 2 LSB position, so easily I will get this divide by 4. So, then what I have to do here, circuit wise or the architecture wise, what will be the architecture? Suppose I am having this squaring circuit, then initially what I have to do, suppose this two terms, that means the multiplier and the multiplicand, they are a and x. So, in one particular circuit, so if I just draw this corresponding circuit, so at that time how it will be? It will be just like, so a into x if I have to do, so that will be minus a minus x whole square divided by 4. So, means this is a square plus 2ax plus x square minus a square plus 2ax minus x square. So, this and this will be nullified, divided by 4 means 4 of ax divided by 4. So, that is nothing but my ax. So, if I just want to draw this particular circuit, so at that time what will be its architecture? It will be just like, so if this is a, this is x. Okay. So, in one particular case I have to generate a plus x. Okay. So, then again I will having another particular circuit which is minus. Okay. So, this will gives me a minus x. Okay. So, now I will have this corresponding squaring circuit. Suppose this is x square circuit. So, this I will get. So, from here what I will get, that is a plus x of whole square. So, again if I just pass this along with another, this is just squaring circuit. Okay. So, if I just pass this value, then again I will get a minus x of whole square. Okay. Then again what I need? I need to do one subtraction of this. Okay. And from here what I have to do? I have to left shift the results of this, left shift, this is right shift by 2 bit, or else what I can write, discard 2 LSB from this particular results. Okay. So, if you do that, then I will get A into x. Okay. So, complexity wise, or if I just try to calculate the corresponding delay for that. So, then if you see that here I am getting that means for the squaring circuit I can optimize it, okay. But here I need two additional, here I need one additional adder, here I need one additional subtractor. If I just say in this particular path I need one subtractor here additional, one subtractor here additional. So, that means by using this particular method, if I want to calculate the that means the multiplication. So, at that time I can get, or I may get, for if I consider more number of bits for this A and x. So, at that time this particular architecture will not give me that much benefit. Why? Because whatever benefit I will get in the squaring circuit, that will be if this particular bit, that means if the length of A and x they are that means more. So, at that time the complexity or the area requirement or the speed requirement for this extra overhead of this adder and subtractor, that will be degrade the corresponding optimization whatever I am getting for this squaring circuit. Okay. So, that is why this particular architecture, okay, this particular structure is beneficial whenever the corresponding length for this A and x, the bit of A and x, they are less. Whenever they are more, at that time this particular architecture is not that much beneficial. Okay. So, that means hardware design of that is not at all advantageous at that time. Okay. So, this is the another method of doing the multiplication using squaring method. So, that you can use in your system. So, apart from that, there are again this multiplication architecture is such a, that means dynamic field. People are doing more research on that for finding out one efficient architecture for designing the multiplication. So, if you find that means literature, you can get there are some Vedic multiplication, basic Vedic multiplication methods are there in the that means in the ancient Vedic era. Okay. So, that particular algorithms now you can map into the hardware, or you can design into the hardware to get the multiplier architecture which will be beneficial in terms of speed or in terms of area or in terms of power. Different aspects you can choose for. Okay. Apart from that, again there are this based on this approximate computing also some of the multiplier has been designed. Means what? In approximate computing, what we do, we intentionally we put some of the error, or we just discard some of the bits, and then we do this multiplication and we pre-calculate those errors. Okay. So, what will be, that means intentionally as I am skipping some of the bits. So, from the beginning we know that because of this skipping of the bits, so what will be the maximum error, or what will be the quantity of the error I can accumulate during that whole multiplication operation. So, at the end whenever we will produce the result, so at that time we will try to calibrate with those errors, that means pre-computed errors, to get the proper result. So, that means as I have reduced the number of bits from the beginning, that means the complexity of the hardware at that time it will be lesser. Okay. But apart from the at that time, at the same time, what I have to remember, that the result that should be correct. So, that means for the corresponding approximation, what will be the error? So, that will be again added at the final edge, final stage to get the accuracy also at the proper level or in an adequate level. Okay. So, that type of multiplier architectures is also available in the literature. People have worked on that, and that is based on this approximate computing, this multiplier design. Okay. So, that type of architecture we are not discussing in this particular class. So, if you need, then I will be just putting it just as a supplementary material in the discussion forum that I will be supplied. Okay. Then till now what we have seen, that the multiplier or the multiplication operation in the considering the number in the in the integer part. So, that means here what we have seen, the number that are like 1, 2, 3, 4, 10, 11, 22. So, those the numbers are basically integer one. Now, suppose in if we see most of the DSP system, okay, in most of the DSP systems, the number DSP system means, suppose if you want to do the DFT, or if you want to do the filtering, or if you want to do the FFT, or if you want to do the any transform like Hilbert transform, cosine transform, or then Hartley transform, So, this kind of transform, they require the coefficient values, or in real time DSP system the coefficient values of these filters or these transforms are basically considering the fact they are in the decimal or the fractional part. That means, mostly they are dominated by the fractional part. If you just see that whenever we are doing the multiplication, we do not know what will be the value for multiplier and multiplicand. So, at that time the architecture is different. Whenever we know that the two numbers are same, so at that time we can do more optimization. Now, another thing is that in FIR filter, most of the, that means the multiplication which is being used in the DSP system, there the values are constant. That means, suppose if I say that okay, this 3-tap filter with this kind of specification, the corresponding filters parameters or the coefficient values, they are fixed for that particular specification. Okay. The same things happen, suppose this let us say 8-point FFT if I ask you. So, the 8-point FFT, the corresponding tweedle factors, they are basically fixed, the values of that will be fixed. So, considering this fact, whenever we need the multiplication operation on those system, so at that time can I do it more optimization? That means, the structure, can I do it more optimized? Yes, I can. How I can? Because the number is constant means I know the corresponding bit values of each of these particular coefficients. Okay. So, considering this fact that now I can optimize the multiplier in a better way. Okay. So, I do not require to use any generic multiplication at that time to do this multiplication on the DSP system. So, if I can use, if I use it, so at that time intentionally or unintentionally I will use more of the area or more of the power, though because I have the provision to do the optimization, because I know the numbers from the beginning as the number is already fixed. So, I can do the optimization or I can play with that. So, how I can do, or what is the, that means at that time how this technique will be, or what will be the techniques to do this optimization, that we will see in the next class. So, thank you for today's class. So, next day we will see this constant multiplication, and then not only constant multiplication, this reconfigurable constant multiplication, how we use and where it is being used, how we can that means come to the optimized circuit, or how we can design it, that we will see in the next class onwards. So, thank you for today.